Lab 1, constant velocity. Jolene Shea. Okay, so for an intro, the purpose of this lab is to observe a motion of an object that's moving at a constant velocity through tracker, and then compare that motion to predicted value calculated from a computational model through the GLOW script. In this lab, we're assuming that there's no air resistance, no friction, and that normal force equals gravitational force, meaning that the object is moving on a flat surface. So when we go into our fundamental principles, Newton's second law is our fundamental principle, and we interpret that as the momentum principle, which basically states that the net external force equals the change in momentum of a system divided by the time over which it changes. And then here are some equations that show that principle. So for the experiment, the object that we are measuring is a tape measure, and that's the object that's rolling. The surroundings is friction, which we consider negligible for this experiment, gravity, applied force, and then anything else. The initial conditions is that the position starts at 0.108 meters, which is where the tracker initially starts tracking the object. And the procedure is that we start by recording the object rolling at a certain distance. Then we import that recording into tracker to find the observed position at specific times. We then create a computational model in GLOW script to find the observed position and compare that to the tracker positions. Then we create a spreadsheet with both the tracker and the computational models and compare these graphs to see if there's any differences. So for the tracker analysis, the video shows that because of the slope of the line, that the ball's moving to the right because it's a positive slope, and that from the graph it seems mostly linear because the line in the graph is linear, which means that we can assume that the velocity you can assume that it's constant. So in the computational model, we apply these same principles, and we see that the position goes positive, so that it's similar to the experimental model that we found. But when we look at the graph from taking the code from GLOW script and putting it into the graph, we see that there is a slight divergence between the computational model and the tracker model, which suggests that our tracker or our computational model might overestimate what is actually going on, which indicates that there are some other forces at play in the actual experimental model. So for our what if question, we can ask, what if we were to flip the axes? How would that change our results? So if we were to flip the axes, then our velocity would be negative, but this does not change the magnitude of the velocity, which ultimately is what we're trying to find because we're trying to see it with constant velocity. And then our observation, so because our computational model overestimates the position of the ball, there are some other factors at play that we can not consider negligible, like friction, which causes the ball to not be as far as our computational model suggests. And then some other potential errors would be human error if the ball was not pushed fully straight, or if the push was too hard, making the velocity not constant, and some GLOW script or computational errors, which includes incorrect calibration, deviation from placing the center of the mass, or misalignment of the axes, and then again surrounding forces like friction and any other opposing forces.